All right, listeners. Looks like you've really outdone yourselves this time. You sent over a whole bunch of physics notes and equations. Looks like we're about to take a deep dive.
Into the world of motion. Two-dimensional motion, to be precise.
Motion in 2 dimensions.
Yeah.
Yeah, this is where I think things start to get a little bit more interesting.
A little more complex, for sure.
Yeah, definitely more complex.
Okay.
But that's the fun of physics, right?
Absolutely. Unraveling the mysteries of how things move. That's what we're here for.
Okay, so before we get too far, what's the biggest challenge when it comes to understanding motion in 2 dimensions? Because it seems a lot more complicated than just, something moving in a straight line.
I think the biggest challenge is wrapping your head around the fact that the motion is happening in two directions simultaneously. So think about, like, if you throw a ball, it's moving horizontally and vertically at the same time.
Right. It's not just like up and down. It's not just left and right.
It's
like
doing both.
it's doing both. Yeah.
Yeah.
Like a curved path. So how do we even begin to make sense of that?
That's where this idea of breaking motion down into its components comes in. So instead of trying to tackle the entire motion at once, we kind of separate it out into its horizontal component along the x-axis and its vertical component along the y-axis.
So we're like pretending that it's moving in two straight lines even though its actual path is curved.
Exactly. And the beauty of that is that motion along one axis doesn't actually affect the motion along the other. They're happening simultaneously but independently.
Okay. So can you give me like a real world example just to help me visualize this a little bit better?
Absolutely. Imagine you're on a train and the train's moving at a constant speed, and you roll a ball across the floor of the train. From your perspective, on the train, that ball is just moving in a straight line, right?
Right.
But someone standing on the platform watching the train go by would see the ball moving in a curved path.
Yeah.
Because they're seeing the combined motion of the ball relative to the train, the train relative to the ground. But we can actually analyze each of those motions separately using this component breakdown.
So it's like instead of solving one really complex problem, we're solving two simpler problems.
Exactly. We can look at the horizontal motion and the vertical motion totally separately, and then we can kind of put the pieces back together to get the full picture.
Okay, that makes a lot more sense. So I'm feeling good about components. Now let's move on to velocity. Now, if I remember correctly, velocity is more than just speed right now.
You're absolutely right. Velocity is a vector quantity, which means it has both magnitude, which is the speed, and direction. So a car traveling north at 60 miles per hour has a different velocity than a car traveling east at 60 miles per hour, even though they have the same speed.
So it's not just how fast something is going, it's also like in what direction.
Precisely. And when we're talking about velocity in 2 dimensions, we have to consider both the horizontal and vertical components of that velocity.
Okay, so how do we actually visualize velocity in 2 dimensions?
Think of velocity as an arrow. The length of the arrow represents the magnitude of the velocity, which is the speed, and the direction the arrow is pointing represents the direction of motion.
So if a ball is thrown upwards, like at an angle, then the velocity arrow would be pointing diagonally upwards.
Exactly. And here's a key point. Velocity is always tangent to the path of motion. So if you think about like a car going around a curve at any given moment, that velocity arrow is pointing in the direction the car is moving at that moment.
Which is tangent to the curve.
Tangent to the curve, exactly.
So even if the car is going around like a circular track and it's going at a constant speed, its velocity is constantly changing because its direction is constantly changing.
That's right. Which brings us to acceleration.
Which acceleration, that's all about changes in velocity, right?
Exactly. Acceleration is the rate at which the velocity changes. And just like velocity, it's a vector quantity. It has both magnitude and direction.
Okay, so acceleration isn't just about like speeding up. It can also be about slowing down or changing direction.
Exactly. Any change in velocity, whether it's the speed changing or the direction changing, means there's acceleration. So even that car going around the circular track at a constant speed, it's still accelerating because its direction is changing.
Whoa, okay, my mind is officially blown. So how do we actually calculate acceleration in 2 dimensions? Is it similar to how we calculate velocity?
It is. So we break it down into its horizontal and vertical components, just like we do with velocity. And we can use those components to calculate the overall magnitude and direction of the acceleration.
I'm seeing a pattern here. Breaking things down into horizontal and vertical parts seems to be the key to understanding motion in 2 dimensions.
It's a really powerful tool. And speaking of tools, calculus plays a really big role in actually calculating a lot of these quantities.
Oh, calculus. Yeah, I was wondering when calculus would make its appearance. I do remember something about derivatives.
You're right. So derivatives help us to calculate velocity from position and acceleration from velocity. But for this deep dive, we're going to kind of focus on the conceptual understanding and how all of these things relate to each other.
Sounds like a good plan.
Yeah.
So can we maybe look at a specific example to kind of see how this all plays out? There's one here about a particle undergoing constant acceleration.
That's a great one to start with. It really shows how we can use the equations of motion to figure out the velocity of that particle at any given time, if we know its initial velocity and its acceleration.
And we would do that separately for both x and y, correct?
You got it. We break down the initial velocity into its horizontal and vertical components, and then we can kind of use those to calculate the velocity at any given point in time. And even though we're breaking it down, remember, that particle is experiencing both the horizontal and vertical motion simultaneously.
It's all about putting those pieces back together, right?
Absolutely. Okay, how about another example? This one here, with the particle moving in the xy plane. This one's interesting because it talks about how the acceleration and velocity vectors can actually have different directions.
Right, and this one really highlights the fact that acceleration and velocity don't have to be pointing in the same direction. Remember, acceleration is about the change in velocity. So even if an object is moving upwards, it could be experiencing a downwards acceleration because of gravity, which would eventually cause it to slow down and change direction.
Okay, yeah, so I'm starting to see how these concepts can get pretty tricky, but also really cool. So are we ready to launch into projectile motion? I've always been curious about the physics behind things flying through the air.
I think we're ready. Projectile motion is a special case of motion in 2 dimensions. Specifically, it's when the only acceleration acting on the object is due to gravity.
So we're talking about baseballs, rockets, those perfectly arched basketball shots? Exactly. And to make things a bit simpler, usually we make a few assumptions. We ignore things like air resistance, and we assume that gravity is constant.
So basically, we're just focusing on how gravity affects the object's trajectory.
Right. And just like before, we can analyze this by separating it into those horizontal and vertical components.
So even though the baseball is following a curved path, we can pretend it's moving horizontally at a constant speed while also moving vertically under the influence of gravity.
You got it. And that lets us use those equations we've already been talking about to predict things like how long it will be in the air, how high it will go, how far it will travel.
Okay, I can see how these ideas build on each other. But I'm guessing projectile motion has a whole bunch of its own equations and a whole bunch more complexity, right?
You're not wrong. There's a lot more to unpack. But I think we'll save that for the next part of our deep dive.
Okay, sounds good. Well, my physics brain is definitely warmed up and ready for more. I can't wait to see what other secrets of projectile motion we uncover in part 2.
Stay tuned. We'll be back soon to explore those equations and really unlock those curved paths and how they work.
I can't wait. Okay, I'm ready for more projectile motion. So last time we left off talking about breaking down projectile motion into its horizontal and vertical components.
And that breakdown, it's really the key to understanding and predicting where a projectile is going to go and how long it's going to take to get there.
Okay, that sounds pretty useful. So what kind of things can we actually predict when we're talking about projectile motion?
So we can predict things like the time of flight,
Okay.
the maximum height that the projectile reaches,
Yeah.
and also the horizontal distance that it travels, which we call the range.
So basically we can figure out the whole path of a projectile just from knowing its initial velocity and its launch angle.
Yeah, pretty much.
And I'm guessing there's some handy equations that help us do that.
There are some very helpful equations. But before we jump into the equations, let's just make sure we're all on the same page about what those terms actually mean. So time of flight, that one's fairly straightforward.
Yeah.
It's basically just the total time the projectile spends in the air, like from the moment it's launched until it hits the ground.
All right, that one's easy enough. What about maximum height?
Maximum height. So that's the highest point the projectile reaches during its flight. So it's kind of like that moment where it stopped going up and then gravity starts pulling it back down.
Okay, makes sense. And then range.
Range. So that's the horizontal distance the projectile travels. So from its launch point to its landing point. Think about like a golfer hitting a golf ball. The range is how far that ball travels along the fairway.
Okay, I've got all those terms down. So how do we actually calculate these things? Because I'm looking at these notes and I see a lot of sines and cosines, which is making me think back to my trigonometry days.
You're on the right track. Trigonometry is definitely a key part of understanding projectile motion. Because remember, we're dealing with angles and components. So sine, cosine, tangent, All of those come in handy when we're relating those different quantities.
All right, I'm ready to put my trigonometry hat on. So let's
Yeah.
start with time of flight. What are the things that affect how long something stays in the air?
I think the two main factors are the projectile's initial velocity and the angle at which it's launched.
Okay, so if I throw a ball straight up in the air with like a lot of force, it's going to stay in the air longer than if I just toss it gently.
Exactly. A higher initial velocity, especially in the vertical direction, means it's going to take longer to go up and longer to come back down.
Okay, and what about the launch angle? Does that play a role too?
Definitely. So for a given initial velocity, the time of flight is maximized when the projectile is launched at a 45-degree angle.
Really? Why 45 degrees? What's so special about that?
So 45 degrees, it's kind of the sweet spot between giving the projectile enough upward velocity so that it stays in the air for a while, but also enough horizontal velocity to actually cover a good distance.
So it's kind of like a compromise between going high and going far.
Exactly. And that's why you see like athletes in a lot of different sports aiming for that 45-degree angle because they're trying to maximize both height and distance. So think about baseball, javelin throwing, even like punting a football.
That makes a lot of sense. Okay, so let's move on to maximum height. So I'm guessing that's also affected by both the initial velocity and launch angle?
You got it. So just like time of flight, a higher initial velocity means it's going to reach a greater maximum height. And again, the maximum height is maximized for a launch angle of 45 degrees.
It seems like 45 degrees is like the magic number for projectile motion.
It's definitely a key angle to keep in mind. But, things can get a little more complicated when you start factoring in things like air resistance or if you're launching the projectile on a slope rather than on flat ground.
Okay, yeah. All right, so let's talk about range. So how is that affected by the initial velocity and launch angle?
So, as you might expect, a higher initial velocity means it's going to have a greater range. Basically, it's just moving faster, so it's going to cover more ground before gravity brings it back down.
Okay, and what about the launch angle? 45 degrees again.
You got it. For maximum range on flat ground, 45 degrees is the optimal launch angle.
Okay, I'm definitely starting to see a pattern here,
Yeah.
but I'm also seeing something in these notes about something called complementary angles having the same range.
Yeah, that's an interesting point. So complementary angles are two angles that add up to 90 degrees. So like 30 degrees and 60 degrees would be complementary.
So what you're saying is if you launch one projectile at 30 degrees and another one at 60 degrees with the same initial velocity, they're going to both land the same distance away.
Exactly. It might seem a little counterintuitive, but the math works out that way.
Wow. But wouldn't they have different maximum heights and different times of flight?
Absolutely. So that's kind of the trade-off. So complementary angles have the same range, but they're achieving it in different ways.
Mhm.
So the one launched at a lower angle will have a shorter flight time and a lower maximum height, while the one launched at a higher angle, it's going to be in the air for longer, and it's going to go higher.
So what does that tell us about like strategy? Let's say you're trying to hit a target that's a certain distance away.
Right. So if you have a couple of different launch angles that will reach the target,
Right.
you can kind of choose the one that's most advantageous for the situation.
So if you need to get it there quickly, you might go with a lower angle, even if it means like a lower height.
Right.
And if you need to clear a high obstacle, then you might go with a higher angle, even though it means it will take longer.
You got it. It's all about understanding the trade-offs and kind of choosing the angle that works best.
This is starting to feel like we're strategizing for a rocket launch. It's really interesting how these equations give us all this predictive power. So are we ready to actually look at some examples and see how these equations work? Let's start with this one, where we have to calculate the time of flight, the maximum height, and the range of a projectile if we know its initial velocity and launch angle.
Perfect. So this is like your classic projectile motion problem, and it's a great way to kind of see how those equations that we've been talking about actually work in practice. So we can take the numbers that are given to us and we can use our trigonometry to find the x and y components of that initial velocity, and then from there it's just a matter of plugging those components into those equations that we've been talking about.
Yeah, and then we solve for all the things we want to know.
Right.
Okay, I think I'm starting to get the hang of this. It's cool to actually see it in action. All right, what about this one? This one's about a projectile launched on an inclined plane.
Okay, so now things are getting a little more challenging.
I was hoping we get up the difficulty level a bit.
But the fundamental principles that we've been talking about, they still apply. The main difference is that we have to adjust our coordinate system to account for the angle of that incline.
So instead of thinking about horizontal and vertical,
Yeah.
we're thinking about components that are like parallel and perpendicular to the plane.
Exactly. We can still break the motion down into those components and use similar equations to analyze its trajectory.
So we can still figure out, like, the time of flight, the maximum height, the range.
Yes.
But the equations are just going to be a little different.
Slightly modified, yeah.
Because we have to account for that angle.
Uh-huh.
Okay, so this is definitely making me think a little bit harder.
Good.
But I'm also starting to get a sense of how powerful these physics ideas are for analyzing, like, real-world situations. Because in the real world, not everything is flat.
Right, exactly. And that's what makes physics so cool, because it really gives us this framework for understanding and predicting how things move, no matter how complex the motion might seem.
Okay, well, I think my projectile motion brain is a little tired.
I can understand that.
So I think I'm ready to move on to a new topic.
Uh-huh.
What's next on our physics adventure?
How about relative motion?
Ooh. Relative motion. I always found that a little bit mind-bending.
It definitely requires a shift in perspective.
But I'm up for the challenge.
Okay, let's do it.
All right, lead the way. Let's see where this relative motion journey takes us. Okay, relative motion. I'm ready to have my mind blown.
It's definitely a concept that challenges our intuition a bit.
So we were talking about, like, how motion can look different depending on where you're standing or how you're moving.
Exactly. Relative motion is all about understanding how those observations change based on the observer's frame of reference.
Frame of reference.
Okay, so it's like there's no absolute motion, only motion relative to something else.
Okay, can you give me an example?
Yeah.
Because I think that would help.
Sure. So imagine you're on a train and it's moving at a constant speed and you toss a ball straight up in the air. So from your perspective, on the train, the ball just goes up and comes straight back down. But to someone standing on the platform, watching the train go by, that ball would actually look like it's following a curved path.
Oh, yeah.
So it's moving horizontally as well as vertically.
So the ball is doing the same thing, but it looks different depending on whether you're on the train or standing on the platform.
Exactly. The person on the train is seeing the ball's motion relative to the train, and the person on the platform is seeing the ball's motion relative to the ground.
Okay, I'm starting to get that. But how do we make sense of this mathematically? Do vectors come into play here?
Absolutely. Vectors are essential for describing relative motion because they capture both the magnitude and the direction.
Right, right. Okay, so remind me again. Vectors, they're like those little arrows that point in the direction of the motion.
Yeah, think of it like an arrow. The length of the arrow represents the speed, and the direction of the arrow obviously is indicating the direction.
Okay, and if we're trying to figure out the relative velocity of two objects, we need to think about both their speeds and their directions.
Exactly. And we can actually use vector addition to combine those velocities and get a sense of their motion relative to each other.
Okay, I think I need a real-world example here.
All right, let's try a classic. Walking in the rain. So the question is, how should you hold your umbrella to stay as dry as possible?
Oh, yeah, this is a problem I face all the time. It's like sometimes it feels like the rain is coming sideways at me.
That's exactly what relative motion is all about. It's not just how fast the rain is falling, it also depends on how fast you're walking and in what direction.
Okay, so we need to consider the velocity of both the rain and the person to figure out the best angle to hold the umbrella.
Right. Think of it like this. The rain has a velocity that's basically downwards, and the person has a velocity that's horizontal, assuming they're walking on a flat surface.
So the person needs to tilt their umbrella, not just straight down, but kind of like in the direction of the rain's velocity relative to them.
You got it. And if they're walking quickly, they're going to need to tilt it forward more than if they're walking slowly.
Okay, that makes sense. Relative motion really is all around us.
It is. Okay, how about another example? Boats and rivers.
Okay.
So imagine you're trying to steer a boat directly across a river, but the river has a current that's flowing downstream.
Okay, I can picture that.
So if you aim your boat straight across the river, that current is going to push you downstream, and you're going to end up further down the river than you intended.
So how do you avoid that? How do you make sure you get to the spot you actually want to go to?
You have to aim your boat upstream at an angle.
Right.
So that the boat's velocity combined with the current's velocity results in a net motion that's straight across the river.
So you're kind of like fighting the river.
Yeah, it's like a tug of war. And we can actually use vectors to figure out exactly what angle you need to aim the boat at.
Okay, cool. All right, you got another boat and river problem for me.
Okay, here's one. What if you wanted to cross the river in the shortest amount of time, even if it means you drift a little bit downstream?
So like speed over accuracy.
Right. In this case, the fastest way to cross is actually to just aim the boat directly across, even though you know the current is going to push you downstream. Because it turns out that by maximizing your velocity in the direction perpendicular to the current, you're actually minimizing the total time it takes to cross.
So the fastest way across isn't always the straightest line.
Exactly.
I'm definitely going to keep that in mind next time I'm in a kayak.
I think that would be wise.
Okay, so just to make sure I've got this right, motion is always described relative to something else.
Yes.
And there's not really one right way to describe it. It just depends on your perspective.
You got it.
This deep dive has been amazing. We've learned so much about motion in two dimensions, components, projectile motion, relative motion.
It's been quite a journey.
It really has. I think my brain needs a break, though.
I hear you. Well, take some time, let these ideas settle, and maybe see if you can spot some of these physics concepts in action in the world around you.
I'm going to try. Well, that's all the time we have for today. Thanks for joining us on this deep dive into motion.
Always a pleasure.
And we'll catch you on the next one.